The moon, our celestial companion, has captivated humanity for millennia. Its presence in the night sky has been a constant source of wonder and inspiration, influencing cultures and civilizations throughout history. Its serene glow in the night sky has inspired countless poets, artists, and dreamers. From ancient myths and legends to modern-day literature and art, the moon has always held a special place in our collective imagination. But beneath its tranquil facade lies a world shaped by violent cosmic events, a testament to the dynamic nature of our solar system. The moon's surface is a record of these events, preserving the history of our cosmic neighborhood. The moon's surface is a canvas etched with the stories of these events, most notably, its craters. These craters, formed by the impact of asteroids and comets, are windows into the past, revealing the turbulent history of our solar system. Craters are the most prominent features on the moon's surface, stark reminders of the relentless bombardment it has endured over billions of years. Each crater, with its unique size and shape, tells a story of a specific impact event. Each crater tells a story, a tale of cosmic impact and the forces that have shaped our celestial neighborhood. These impacts have not only shaped the moon's surface but have also influenced its geological and thermal evolution. These cosmic scars provide us with invaluable insights into the history of our solar system, the formation of planets, and the very origins of life itself. By studying the moon's craters, scientists can learn about the frequency and scale of impact events in the early solar system. The moon, with its silent craters and ancient plains, holds secrets that we are only beginning to unravel. Its surface is a treasure trove of information, waiting to be explored and understood. As we delve deeper into the mysteries of our celestial companion, we gain a greater understanding of our place in the cosmos and the intricate web of connections that bind us to the universe. The moon, our silent witness, continues to guide us in our quest for knowledge and exploration. Craters are not unique to the moon. They are found on planets, moons, and asteroids throughout our solar system. These craters, often seen as mere blemishes, are actually the result of violent and dramatic events that have shaped the surfaces of these celestial bodies over billions of years. Each crater tells a story of a collision, a moment when an asteroid, comet, or meteoroid met its end in a fiery impact. These cosmic scars are formed by the impact of asteroids, comets, and meteoroids, celestial wanderers that hurtle through the vastness of space. These objects, often remnants from the formation of the solar system, travel at incredible speeds, sometimes tens of kilometers per second. When they collide with a planet or moon, the energy released is equivalent to millions of tons of TNT, creating a crater that can be hundreds of kilometers wide. When these objects collide with a moon or planet, the energy released is immense, creating a crater. The impact generates shock waves that travel through the surface, fracturing the crust, and excavating material from deep within. This process not only forms a crater, but also throws up debris that can travel great distances, sometimes even escaping the gravitational pull of the body and becoming meteoroids themselves. Imagine a rock thrown into a pond. The impact creates ripples that spread outward from the point of entry. Similarly, when a cosmic projectile slams into the moon's surface, it generates shock waves that radiate outward, fracturing the lunar crust and excavating a bowl-shaped depression. These ripples in the lunar surface can tell us a lot about the force and direction of the impact. Similarly, when a cosmic projectile slams into the moon's surface, it generates shock waves that radiate outward, fracturing the lunar crust and excavating a bowl-shaped depression. The size and shape of the crater depend on various factors, including the size, speed, and angle of impact of the impacting object, as well as the composition of the lunar surface. Larger impacts can create central peaks or multiple rings, adding to the complexity of these features. The size and shape of the crater depend on various factors, including the size, speed, and angle of impact of the impacting object, as well as the composition of the lunar surface. Some craters are simple bowl shapes while others have central peaks or even multiple rings. These variations can provide clues about the nature of the impact and the properties of the surface material. Craters are not merely holes in the ground, they are windows into the past, providing us with clues about the history of our solar system. By examining the layers of material exposed by the impact, scientists can learn about the geological history of the moon and other bodies. The distribution and frequency of craters can also reveal patterns of past bombardment, helping us understand the dynamic processes that have shaped our solar system. By studying the size, distribution, and composition of craters, scientists can piece together a timeline of cosmic events and gain insights into the bombardment history of the Moon and, by extension, the Earth. This research not only helps us understand the past but also prepares us for the future as we continue to explore and protect our place in the cosmos. Simple craters are the most common type of impact crater found on the Moon. They are typically small, bowl-shaped depressions with a raised rim and a depth-to-diameter ratio of about 1:5. Simple craters are formed by relatively small impactors, ranging in size from a few meters to a few kilometers in diameter. The impact process for simple craters is relatively straightforward. The impacting object vaporizes upon impact, and the energy released excavates a cavity in the lunar surface. The ejected material, known as ejecta, is thrown outward, forming a blanket of debris around the crater rim. The shape of a simple crater is determined by the physics of the impact and the properties of the lunar regolith, the layer of loose, unconsolidated material covering the Moon's surface. Simple craters are valuable records of past impacts. Their size and distribution provide insights into the population of small objects in the inner solar system, while their morphology and the characteristics of their ejecta blankets offer clues about the physical properties of the lunar regolith. Section 4. Complex craters unveiling hidden depths. Complex craters, as their name suggests, are more intricate in their structure than simple craters. They are typically much larger, with diameters exceeding several tens of kilometers, and exhibit a range of complex features such as central peaks, terraced walls, and multiple rings. These complex structures are a testament to the immense energy released during the impact of larger objects. The formation of complex craters involves a more dynamic process compared to simple craters. The initial impact creates a transient cavity that collapses under its own gravity, leading to the uplift of the central peak and the formation of terraced walls. The multiple rings observed in some complex craters result from the outward propagation of shock waves through the lunar crust. Complex craters offer a glimpse into the deeper layers of the Moon's crust. The uplifted central peaks can expose materials that were once buried kilometers below the surface, providing valuable information about the Moon's internal structure and composition. Section 5. Water ice on the Moon. A discovery of cosmic proportions. One of the most exciting discoveries in recent lunar exploration has been the confirmation of water ice on the Moon. This discovery has opened up a new chapter in our understanding of the Moon and its potential for supporting future human missions. The presence of water ice is not just a scientific curiosity, it is a game changer for space exploration. This finding has profound implications for future lunar missions, as it could potentially provide a vital resource for human explorers. Imagine a future where astronauts can extract water directly from the lunar surface, reducing the need to transport heavy supplies from Earth. This would make long-term lunar habitation more feasible and sustainable. Water ice could be used for drinking, oxygen production, and even rocket fuel, reducing the need to transport these resources from Earth. The ability to produce rocket fuel on the Moon could also serve as a stepping stone for deeper space exploration, enabling missions to Mars and beyond. This would mark a significant milestone in human space exploration. The discovery of water ice was made possible by advanced lunar missions, such as NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1 spacecraft. These missions have provided invaluable data, helping scientists to map the distribution of water ice across the lunar surface and understand its abundance. These missions carried instruments capable of detecting the unique spectral signature of water ice, even in the permanently shadowed craters at the lunar poles where temperatures are cold enough to preserve ice for billions of years. The technology used in these missions represents the cutting edge of space exploration, showcasing human ingenuity and the relentless pursuit of knowledge. The presence of water ice on the Moon raises intriguing questions about its origin. How did this water get there, and what does it tell us about the history of our solar system? These questions are driving new research and exploration efforts, as scientists seek to unravel the mysteries of the Moon's icy deposits. Some scientists believe it was delivered by comets and asteroids that impacted the Moon early in its history, bringing water from the outer reaches of the solar system. These impacts would have deposited water ice in the Moon's shadowed craters, where it has remained frozen for eons. While others suggest it may have originated from volcanic outgassing or interactions with the solar wind. volcanic activity could have released water vapor, which then condensed and froze in the cold, lunar environment. Alternatively, the solar wind could have implanted hydrogen ions into the lunar soil, which then combined with oxygen to form water. Each of these theories offers a fascinating glimpse into the dynamic processes that have shaped the moon over billions of years. Section 6. Volcanic Surprises, the Moon's Fiery Past. While the Moon is often perceived as a cold, dead world, recent discoveries have revealed a more dynamic past. Evidence of past volcanic activity has been found in the form of vast plains of volcanic basalt, known as maria, and volcanic domes, which are mounds formed by the eruption of viscous lava. The volcanic activity on the Moon is thought to have peaked between 3 and 4 billion years ago, when its interior was much hotter. The maria, which cover about 16% of the lunar surface, were formed by massive outpourings of lava that filled impact basins. The discovery of volcanic domes suggests that the Moon's volcanic activity may have persisted for a longer period than previously thought. The study of lunar volcanism provides insights into the thermal evolution of the Moon and the processes that shaped its interior. It also raises questions about the potential for future volcanic activity, although most scientists believe that the Moon is now geologically inactive.